Hello, welcome to Electronics Education. I'm Vincent Chang. So today I'm going to continue the lesson on the practical operational amplifier and introduce another DC problem of a real operational amplifier, which is the input bias current. Operational amplifier, input bias current, and the input offset current. So let's start with the model of the input bias current. Here's the operational amplifier, and this is the model. So you use a two current source to represent the issue of the input bias current. But why we have to add the two current source to represent this issue? Again, this question can only be answered completely in the area of analog integrated circuit. But again, I assume that this is not the course for analog integrated circuit. But I still want to touch a little bit, show you, to go a little bit deeper to let you know where these two current sources coming from. So let's look at the 741 operational amplifier. And the issue comes from the input, again, differential stage, the differential amplifier. The left-hand side is the non-inverting, the terminal A. The right-hand side is inverting, terminal B. So again, if you connect the two input terminal to DC ground, again, the ground is the common terminal for the two power supply. The positive 15 volt and negative 15 volt, there's a ground point. That ground is the blue ground. And then what? Then you will see a current. Because when the transistor is on, is turned on, there will be current. There will be a current. So if the current is zero, that means the transistor is cut off. So how can an amplifier work when it's frozen, when it's cold, when it is cut off? So if we want the transistor to amplify to working, the amplifier is working, you have to turn the transistor on, right? And so the transistor is get hot, is working, is warm, right? There's a current. So that current is the source for this so-called input bias current, the bias for the input transistor of the differential amplifier. And then in the data sheet of a real op-amp, then you will see two specs. The first one is called input bias current, which is defined as the average value of these two current. And then the second data you will see on the data sheet is the difference of these two current. IB1 minus IB2 is called input offset current. Again, that's the definition for the input bias current and the input offset current. So now, I talk about the model, then let's move on to talk about the effect. What kind of effect you will see and coming from if this issue is considered. Let's again consider a non-inverting amplifier. The non-inverting and amplifier. And now let's replace the op-amp with the input bias current model. So just plug in two current source to represent now the issue is considered. The input bias current issue is considered. And then what? Then it's easy, right? Virtual ground. And then zero current. And then IB1, like this. the output voltage is 0 plus a potential of voltage increase like this. If you can remember, toward the end of the previous lecture, we tried to suppress. We saw an issue from the output offset voltage coming from the input offset voltage. And now there's another force, another issue coming from the bias current. Try to keep pushing the output offset voltage up, right? So now I'm going to teach you one of the popular way to suppress, to compensate, to eliminate the output DC offset voltage coming from the input bias current. So the way is we use a resistor called compensation resistor. The issue is how to eliminate the output DC offset voltage coming from the input bias current. How to eliminate the output DC voltage caused by the input bias current? So we use this, a compensation resistor R3, additional resistor R3. So so let's do a circuit analysis first. And then I will explain how to choose the value of this compensation resistor. So step 1, find the non-inverting terminal voltage. Easy. And then step 2, virtual short. And step 3, find the current. IB to R3 divided by R1. What about step 4? KCL, right? So KCL. So based on the KCL at node B, then the blue current equals the IB1 minus step 3 current, the green current, right? So the step 5, then here comes the output voltage. It's going to be step 2's voltage plus step 4's blue current times R2, like this. Let's say that again. The step 2 voltage plus, because you're against the current, so voltage increase by the voltage drop. So the blue current times R2, right? Very clear. So now you see this. Now you see this. Assuming the two currents are equal. Let's assume the two currents are equal. Then what? Then you will see this. To express the output offset voltage, right? Then if someone asks you how to choose a proper value for achieving the best outcome. The best outcome is we don't want to see the output DC offset. So then we let VO 0, then what would you get? You'll get this, right? You'll get this. It's the parallel of R1 and R2. It's the resistance you stand on the inverting terminal. You stand your foot on the inverting terminal and looking outward and get these two resistors and try to get the parallel of these two. One is R1, the other one is R2. Takeaway. The compensation resistor. The value, how to choose a proper value, try to kill to eliminate the output offset voltage caused by the input bias current. It's the resistance of you stand on the inverting terminal and get the resistance, the effective resistance, which is the parallel combination of R1 and R2. So we are approaching to the end of this lecture. This is also the end of the operational amplifier series. So I hope you receive something from this series. If necessary, if you need it, maybe go back to watch some of the lecture you feel most interested. So I look forward to seeing you in the other courses or lecture video. Thanks for watching.